Okay. Okay, if I could have your attention, everyone. It's my privilege to introduce today our speaker, Tony Stark, who I've known and admired for 30 years as a superb instrumentalist, a galactic astronomer, and also recently a cosmologist. Tony got his undergraduate degree from Caltech in 1975, and then 4 years later his PhD from Princeton under Arno Penzias. He joined the Radio Physics Research Group at Bell Labs, led by Bob Wilson, and he conducted pioneering work on millimeter wave instrumentation and conducted large-scale surveys of the galactic interstellar medium. He was PI in particular of a the landmark Bell Labs H1 Galactic Survey, carried out with a 20-foot horn antenna of CMB fame at Bell Labs. Because of the exceptionally clean beam of that instrument, the Bell survey is really the gold standard still today for determining the accurate column densities at high galactic latitudes. And this publication has been cited over 1,100 times. Tony came to the CFA in 1991, and he is currently a senior scientist with the R&G division. Now, it is no exaggeration to say that Tony was one of the pioneers of Antarctic astronomy. He made his first trip to the South Pole almost 30 years ago, where he took preliminary measurements to establish that the Antarctic Plateau was a superb astronomical site. Soon after, he co-founded the Center for Astrophysical Research in Antarctica, CARA, and later chaired the South Pole Users Committee for 7 years. To date, he's been to the South Pole 25 times, both as PI and designer of the Astro sub-millimeter wave telescope, which was operated at the pole for over 10 years successfully, and more recently as co-PI of the South Pole Telescope, which you'll be hearing more about today. Tony is actually such a household name in Antarctica that he was given an honor which at first I found hard to believe. Now, I know it's totally cool that one or two of you here probably has an asteroid or a comet named after you, but there is in fact a mountain range in Antarctica which is named after Tony Stark. It is called the Stark Ridge. It runs for 11 miles from Hunt Mountain to Starshot Glacier. And if you Google the Stark Ridge, you will actually see a picture of the mountain. But Google reports that a street view is not yet available. Now, I'm sure that Tony can tell you much more about the ridge, but he's mainly here today to tell you about cosmology from the South Pole Telescope. Tony.
Oh, well, thank you. Okay, well, I thought, yeah, this looks good in the dark. This is a real picture taken by the second-year winter rover Keith Vanderland at the pole. The South Pole Telescope Consortium is now fairly large. I think it's about 70 people. Here's a picture of a lot of us, and there's me there's me, and Brian Stalder, who's in the audience, and a lot of people from the University of Chicago and other institutions. Our little shield is down here. So if you don't show this next slide, they take away your license to do observational cosmology. So I have to show it. The point is that in the 1 minute refresher course on cosmology, remind everyone that because the speed of light is finite, by looking out in distance, you can look back in time. And you can, in fact, look all the way back to the Big Bang, which appears to us to be only 13.7 billion light years away and surrounds us in all directions. The light, if you got in a wormhole and went out in any direction 13.7 billion light years and then looked back at the Earth, you would see the atoms that are now in our bodies and the electrons and particles emerging from the Big Bang in our location. So you can, in fact, see the beginning of the universe, except that it is opaque to radiation until the emission of the cosmic microwave background at about 300,000 years, 400,000 years after the Big Bang. At that point, the universe is neutral for a long time, and then it reionizes after the first stars and galaxies form, and structure grows, clusters grow, and eventually you get to the current time. So in the talk today, I'm going to talk about a bunch of stuff that's on this picture. At the very earliest time, there's the primordial B-mode detection, which is perhaps the one best hope for finding out something about the era of inflation in the first, well within the first nanosecond of the Big Bang. The CMB itself, which has structure that is caused by quantum fluctuations at an earlier time, and then those perturbations grow to actually become the structure of the universe that we have today, and in particular, the baryon acoustic oscillation that we had a talk about a couple of weeks ago. The structure grows, and then there are the first small galaxies, which we will talk about a bit. At some point, neutrinos were relativistic, and then they, because of the expansion, they're cooled off and they slow down. And at the present time, some small fraction, a few percent, of the dark matter is in fact neutrinos. And that transition from a relativistic fluid to a non-relativistic fluid is one of the things that we have some possibility of detecting. So mention that. The era of reionization, we have something to say about that. And then in all of this material in between the galaxies and the clusters of galaxies, they, the gravitational potential from that structure causes lensed, gravitational lens distortions of the cosmic microwave background. And we're now starting to detect that, and that will become a big deal in the next decade or so. And finally, close to home, the South Pole Telescope is a station in the Event Horizon Telescope, which will look at our immediate neighborhood, the galactic center. Yeah. So why the South Pole? Well, the main thing about the Antarctic Plateau, it's high. It's over 3,000 meters, and in places, Dome A, over 4,000 meters. But the main thing is that it's cold. And if it's cold, it's dry, because cold air simply cannot hold much water vapor. It is, in fact, supersaturated or saturated with water vapor almost all the time, but saturated at a temperature of minus 65 or minus 80 centigrade is essentially no water vapor at all. And water vapor at millimeter waves is the main thing. Simply having noise which is constant injected into your system is something that can be overcome by integrating down. If you integrate longer, you'll get a better result. But the water vapor comes in blobs, also known as clouds, in the atmosphere and move across your aperture and cause 1 over F noise, and 1 over F noise does not integrate down. So the extent to which it's 1 over F, you do not get a result. You can observe as much as you like, and you can average as much as you like, and it will not converge to a result. And that's what happens essentially everywhere else on Earth, except South Pole, which is very, very dry indeed, especially in the winter. So for millimeter wave observations with current technology detectors, I mean, this is somewhat specific, but it's relevant. The South Pole really is not much worse than space. Even in space, there's 3K of background noise from the microwave background. So if you had a super, super duper bolometer, which is way better than ones we've got, it wouldn't necessarily be all that much more sensitive, because you've got this background noise filling your system at 3K no matter what you do. And we can get down to a few times this by careful optics at the South Pole. And there's not going to be a 10-meter class CMB telescope in space for the foreseeable future. You really need a 10-meter aperture to resolve 1 arc minute. That's just physics. And when I was an undergrad, I worked on a project with Bob Layton at Caltech, where the idea was that we were going to build these reflectors, and you put these 10-meter reflectors together, and then you'd shoot them up in the space shuttle, which was just in the planning stages back then, and you take these pieces of telescope out, and like some kind of 1950s science fiction guy, you'd get your wrenches out, and you'd put this thing together, and you'd have a 10-meter telescope in space called Large Deployable Reflector. And Large Deployable Reflector and the Large Space Telescope were the two big hopes of the 1970s. Large Space Telescope turned into the Hubble, got a lot smaller and turned into the Hubble. And Large Deployable Reflector is yet to happen, but I assert that everything we had hoped for with Large Deployable Reflector and more is now being done with South Pole Telescope, and uniquely by South Pole Telescope. If you want to know more about site testing or the very fraught astronomical politics that related to that site testing, you can ask me later. So here's a summary, some quick pictures of 3 decades of development of South Pole as an astronomical site. Here is a bunch of guys, including me, Mark Dragavan and Bob Pernick from Yerkes Observatory, and Martin Pomerantz, who has a building named after him at the South Pole, trying to do CMB with a horn reflector and a bunch of crates and some stuff brought in by airplane, just standing around on the Antarctic Plateau in 1986. The only real conclusion from this was that the sky was really good and that we should try again. And by 1988, we did indeed try again. There was an expedition set up with these Jamesway lab tents. If you looked at these tents carefully, there were stamps on them about how they had been deployed during the Korean War. And then shipped to Antarctica, they're basically a couple of layers of canvas with some insulation in between and wooden ends. Here's a picture inside what they looked like. We actually spent the first week nailing in the floor so that it wouldn't be so cold and building our workbenches. But these actually, it's an interesting bit of scientific history that 2 of the instruments, Jeff Peterson's instrument, actually detected the peak in the power law of the microwave background and published it before anybody else, but they don't get credit for it because it was before Kobe, and Kobe got the credit. Here's a telescope near and dear to John Kovac's heart, the Python CMBR telescope, and Mark Dragavan, who was my postdoc, who was the PI for that project. John Kovac was famous for being able to grab a liquid nitrogen tent and haul it over his shoulder and walk up these steps and transfer liquid helium in the middle of the winter all by himself, to everyone's amazement. This is Astro. I realized that we needed a prototype. We needed to prove that we could do long-term, full, year-round, high productivity observations with a sub-millimeter red telescope. Designed and built this telescope, Astro, which operated for 10 years. There's the old South Pole Station, the dome, that's now gone. And this was an offset instrument, and in a lot of ways a prototype for SPT. This is a big communications antenna, a 9-meter communications antenna that was built at the pole just to carry data out. And here are some installations of the DAISY. This was John Karlstrom's instrument that really nailed down the 1 degree peak in the power spectrum of the CMB and did the first detection of E-mode polarization in the microwave background. Here it is sitting on top of the Pomerantz laboratory. You notice that these buildings over the years start getting drifted in. It was up on stilts a couple pictures back, and now it's drifted in. Here's a nice picture of Daisy looking toward Astro, and then the old dome and tower of the South Pole Station. The runway runs across like so. And then one of the significant microwave background telescopes of the previous decade is Viper, and here it is being redeployed on its site, looking a lot like a small version of SPT. This is Bill Holtzaffel at Berkeley. So we have large heavy equipment things at Pole, and can do quite a lot of logistics. This is a bit of an interesting museum piece. I dug this out of my computer files. This drawing was actually made before SolidWorks, obviously, by Smithsonian Central Engineering and paid for by Irwin. And here's a proposed 10-meter cosmology telescope attached to building, and blink back and forth a little bit. We've actually made it happen. So 10 years later, first light, 2007. And here's a picture of the dark sector. So this is kind of the end of the tour, but there's a bunch of telescopes, and now there's BICEP and there's Keck. Here's the last piece of the Astor building disappearing under the snowpack, and the telescope is gone at this point, and the South Pole telescope has just been put in and commissioned. So here's an aerial picture of the whole thing. This is the new station, the runway, and then if you work out here in the dark sector, you tramp back and forth this kilometer routinely in order to go from the logistics of the South Pole Station to the experiments out here. And here's a picture of BICEP. Somehow in all of this publicity last year, every time they showed a picture of BICEP, there was always a picture of SPT in it. So here's SPT. Okay, so enough of the tour. Well, here's some pictures from the inside of the SPT showing that it's a pretty hefty operation. The current receiver, the receiver that's in there now and was the first and second generation receivers, had this huge dewar. It's the size of a Volkswagen. This is the detector dewar with a pulse tube refrigerator on it. And in here is the detector array, which is at 200 millikelvin. And it's being attached to this dewar, which has the secondary mirror. The secondary mirror in this case is maintained at 10 Kelvin. And then the whole thing is hoisted up. See the prime focus cabin here at the end of the boom comes down and mates with the building, and you can then just crank the receiver system up with the chain hoist up into where it belongs. And here it is installed with a bunch of its electronics. It's a pretty major deal. This is the old system, and I'm going to talk about the much better system that will replace it. So one of the things about SPT is the optics. All of the optics are offset, so there's only three elements. So there's the detector. There's a very thin plastic positive lens here, which flattens out the beam. And then this prolate spheroidal mirror that has a focus here and a focus there, and then a paraboloid. And the point is that none of these optics are in the way of any of the other optics. And from the detector, here's the detector, here's that lens, the mirror is cold, and the part of the beam that spills over falls into an absorbing trap, which is also at 10 Kelvin. So that's how we deal at the present time with stray radiation, how we keep the background down. One nice thing about this configuration is you get a focus at near the prime focus here, and that means you can have a vacuum window which is not too gigantic. I mean, a lot of the issue with all of this is that you want a very large field of view. You want a field of view which is actually 2 degrees across in order to get enough beams on the sky, right? Your beam can never be smaller than 1 arc minute. And so if you want tens of thousands of beams, you need a very large field of view. And if your magnification is too high, for example, if you move this focal point down here, you would find that instead of your image being 20 centimeters in diameter, it would be more like 2 meters in diameter. And you would have to cool a 2 meter diameter thing to 180 millikelvin, and that's just, you can't do it. So that's the reason for this optical design. And this is the very first, this is the first generation receiver system. So there's 6 different pieces of bolometer, each with like 128 bolometers on it, done by photolithography. So the ability to make bolometer detectors of good quality by photolithography has allowed this whole thing to run away and have thousands or tens of thousands of detectors. Okay, so how do we do observations? We're going to almost up to the data. So you can't simply stare at one spot on the sky. You have to do a differential measurement. And classically, this was done with a chopper mirror. So you chop between 2 positions on the sky with a moving mirror. The original design for SPT had such a mirror, and then with the experience with Viper, we actually found that it was not necessary, that we could do like the satellites do and have everything in the elevation structure of the telescope be fixed and simply move it in azimuth on the azimuth bearing and move it back and forth, and we would get enough differential movement of the features streaming by the detectors that you could actually make a detection. So these maps are built up. We take 100 square degree section at a time, which is about 10 by 10 degrees on the sky, and remove the array back and forth over a period of a couple of minutes, and then we go step a little bit in declination again, and step again, and do this 10 by 10 map over a period of perhaps 8 hours, and then we do it again, and then we do it again, and then the liquid helium 3 runs out, and there's a period where you have to redo the refrigeration. You bring it up and you do it again. So you do this 100 square degree field for about a month, and you get to the sensitivity you need. So now I'm going to show you that this actually works. Here is some actual data. In cosmology, people often are not sufficiently careful about what is actual data and what is simulated data. But this is actual data from actual WMAP. And this is what it looks like. This is the best they have done. And in the exact same place, this is what Planck has done. So clearly, they're seeing the same thing, only Planck sees it better. And then the same place, this is what SPT sees, which is, again, the same stuff, only, again, way better. And one thing you see, because we have a 10-meter telescope, is that you're starting to pick up point sources. These look a bit like stars behind clouds, but actually they're in the foreground, of course. And there are these dark things, and that's Sinyaev's Elvidge Effect. So if you, so let me just blink that again. So we'll start from WMAP, go to Planck, and then SPT pole. So these are totally independent data sets. Clearly we know what we're doing, and the noise here is very low. There's some striping, And in fact, the production of this map is not optimal. Doing a 100 square degree map is a couple of weeks of CPU time. I developed a more optimal, actually an optimal algorithm that's better than the one we're using, but it's 10,000 times slower. And so we haven't actually used that. And that would get rid of like the striping, and it would, you know, clean up a bunch of stuff and make the point spread function a little better. But it's not a huge improvement, and we don't want to wait 1,000 years to get our data. Maybe someday when there's even faster computers, we'll be able to take this data and process it. So you filter out the large-scale things, and you start seeing the points. So here's primordial CMB, and then the positive pointy things are of two types. One type is a sort of an infrared galaxy, often fairly close, within Z of 0.1 anyway, and you generally showing up even on the IRAS survey. But the other half of them are extremely interesting because they are bright at millimeter waves at 3 millimeters only because they are lensed. And so here's an example. This is the Hubble picture, and that shows an elliptical galaxy, which is actually in the foreground. And then behind it, ALMA shows that there's this dusty sub-millimeter galaxy at Z of 3 behind it that's being lensed. And this is only broken up into almost an Einstein ring. Some of these things have near perfect Einstein rings. I will talk about that again briefly a bit later. And finally, there's Sunyaev's Elvidge effect. If you properly treat these dark spots, which I'll talk about in a bit, they become cluster candidates. And if you then take a big optical telescope like Magellan and integrate for 10 minutes or maybe even an hour, you will find a cluster of galaxies. And that is one of our main things, one of the things we really proposed for. Okay, so far, since 2007, we've done a bunch of surveys. I don't know, the details are perhaps not of interest, but so there's this main SPTS-Z field, and that's the basis of essentially all 35 SPT papers to date. There's deeper data in two fields, and SPT Pol Deep has the second generation detector and has polarization. The first generation detector was unpolarized and had no polarization sensitivity. Second generation is a polarization detector that only works at 95 and 150 gigahertz. And then the new detector system, which we are currently in the process of assembling, will work at all three frequencies and do the whole job way, way better. So I'll get to that. One important point here is that the entire region of the main SPT survey is also covered by the dark energy survey, which is GRIZ photometry done with a 4-meter telescope, and to a depth which is pretty good for us, a depth which gets probably 60–70% of possible cluster candidates. So the data is already in the can, and you just have looked up on a computer. For the higher redshift stuff, that is an issue, and we've got to go to infrared telescopes or integrate much more deeply with, for example, PISCO, in order to verify them. So this is a summary of the 5 kinds of SPT science. So the main thing we've done, and to some extent, is really finished. I mean, you can see the beginning of the end of the golden age of cosmology observations now. And this stuff, as I'm about to show you, is basically done. It's the properties of those ripples in the microwave background and what they mean for cosmology. There's a whole methodology which has become a whole thing with Monte Carlo, maximum entropy fitting, Bayesian models. It's a whole lot of very complicated statistical machinery, and I think it's well, to some extent, it's basically determined by the current power of current computers. Right? If you tried to do that stuff 20 years ago, you couldn't do it because you didn't have computers that were powerful enough. And if you, with the computers that are readily available today, it's just possible to do it. But basically, all you're really doing with all of this huge amount of computer time is finding the minimum in a multidimensional space. So you set up your problem as a linear fit problem, and with say 20 dimensions, and you want to find in this 20-dimensional super tesseract what is the point at which the value is minimum. And that's a very, very hard problem, actually, although conceptually it's simple. And these techniques, all these techniques are really doing is doing that. And so all of this machinery you hear about that seems quasi-incomprehensible and very, very difficult, all it's really doing is this very simple thing. It can be simple because the main assumption behind the reduction of this data is that the only thing that matters about the cosmic microwave background itself is the power spectrum. The actual, whether this point is actually hotter than that point is not of interest. And so there's no information in the phase of the Fourier transform. And so all you have to do then is see if the power spectrum, the square of the Fourier transform, or the cross correlation between two distributions actually matches the theoretical prediction. And that's what's going on with all of these things. And then using Bayesian methods, you can take all of these various methods that are used from all of these different instruments and combine them into a single gigantic multi-parameter model of the universe, and that's going just exquisitely well. There's not a lot left to be done on that. Okay, so the second thing we do is discovery of these high redshift lensed galaxies. These are absolutely grist for the mill for ALMA. They're 10 to 30 times brighter than they would be otherwise, which makes them 100 to 1,000 times faster to observe than they would be otherwise. And on ALMA, you can see these things in really stunning detail. You could actually do, in some ways, more with the interstellar medium of these galaxies at Z of 5 than you can with the molecular clouds in our galaxy, because in part the redshift has shifted the interesting submillimeter stuff down into the millimeter, and you can really get at it with ALMA, which is, one heck of a telescope. Then there's the clusters of galaxies thing. This is the main thing we proposed for. So the density of clusters as a function of mass and redshift is a very important constraint on cosmological models, particularly the dark energy, the history of the dark energy, and the property of neutrinos. What mass, the mass of the neutrino, which is of course very small, determines the epoch at which the neutrinos made this transition from relativistic to non-relativistic, and that occurred near the beginning of the era of galaxy formation, galaxy cluster formation. And so by the statistics of galaxy clusters, you can actually determine the mass of the neutrino more accurately than the particle physics can. They haven't quite realized this yet, but it's a thing you can do. So, and finally, lensing of the cosmic microwave background can be detected as a contribution to B-mode polarization. And from this, you get the lensing potential of the cosmic microwave background. So the cosmic microwave background, in particular, the B-mode polarization of the cosmic microwave background, is distorted on the scale of arc minutes in a way that you can reconstruct. And that allows you to determine the mass distribution of the screen that is between us and the cosmic microwave background, and it calibrates that mass in a very fundamental way. This will be a big deal because it's going, we're just starting to be able to do this, but with the new sensitivities, this will become an easy and really high quality result. And then finally, the SPT is an element of the Event Horizon Telescope, the one that gives you almost all of the north-south baselines. So now I'm going to talk a bit in detail about the cosmic microwave background analysis and kind of by way of history over the last decade or so. So back in, way back in 2002, 10 years after microwave background anisotropy was detected by COBE, this was the state of things. This is your classic power spectrum versus angular frequency. So what we've done here is we've basically taken one of those pictures, those gray pictures with the lumpy stuff in it, and Fourier transformed it and squared it, right? And then that gives this function. And what this says is that the brightest lumps occur at a scale of about 1 degree, and that there are these other things. This gets a lot better in the next slide. But these are the 2002 results. Akbar and Daisy were South Pole instruments. Boomerang was an Antarctic instrument. So there's a lot of Antarctic stuff in there. And as I mentioned, this peak was actually detected by White Dish by Jeff Peterson back in 1989, and published, but no one gives them credit. So this is the status from 3 years ago, and with WMAP. So WMAP does the large scale, and SPT does the small scale, and now you can see the main peak very clearly, and then the subsidiary echoes that provide more detailed information about the relativistic species, et cetera. So, and then finally, the current status of things. This is the current status. So now we've got Planck. The Planck values are infinitesimally different from the WMAP values with the latest recalibration. And out here at the scale of several arc minutes, the only act left in town is SPT, excuse the pun, and everything is in remarkable agreement. This lumpy thing is not, it's a fit, but it's a fit that is constrained to be consistent with lambda cold dark matter, and determines omega baryon and the total mass density of material that's not dark matter and not dark energy to a remarkably high accuracy. So this is kind of a done deal here. And in fact, with SPT, we go to very much smaller scales. So here's the scale. So there's 1 degree and 10 arc minutes. And down here, 1 arc minute, SPT is all alone because none of these other instruments are anything like 10 meters in size. What happens is you've got this microwave background and these echoes that give you the baryon acoustic oscillations. And then at some point, around 5 arc minutes, you start getting Elvidge Effect, which I will talk about in a minute. And then here, on the very small scale, are all the point sources. So they're all of the radio galaxies, and then the Elvidge Effect from the clusters of galaxies. Well, the Elvidge Effect, yeah, well, it has power all through here. This, of course, will get even better yet, but aside from the interesting shape here, which tells you something about when the era of recombination occurred, this is kind of, again, a done deal. So the new thing is polarization, and here's a summary of everyone's polarization power spectrum. So in this case, you can just take, the E mode polarized power and look at that as a function of scale and compare that to cosmologies, and everyone's getting in pretty good agreement. And again, down here at the small end of things, everything is SPT. Right, so SPT really is telling you about the small scale of things. It's actually, we're not entirely sure how well we can do the big things, right? It's much easier to determine whether two spots that are very close together on the sky are a microkelvin different in brightness than it is to tell whether this spot and that spot are a microkelvin different in brightness, which is what BICEP does. So we weren't sure how far out we could go and still get coherent, sensible measurements of how far into the large scale we could go. But I think, as it turns out, by experience, not by prediction, that we will in fact be able to eventually see the tensor scalar ratio R. So here's some very preliminary data of actual B mode versus B mode correlation on the sky, and then you take this and Fourier transform it and you get a B mode thing. And so now, see here, we're in B mode, we're in early days yet. Here's the famous BICEP result, which we've heard so much about. And SPT, we haven't yet we haven't published anything out here, but the preliminary trials look pretty good, and we probably will be able to get out here eventually, particularly with the new receiver. So, cluster science. Oh no, this is the high redshift galaxies. So the distribution of number of sources versus brightness in millijanskis. If there were no lensing, the submillimeter galaxies, the dusty galaxies at high redshift, would give you that. What we in fact see is this plus, now with SPT for the first time, that. And all of these things are lensed objects, and you see here that they're partly Einstein rings. In future, with ALMA, there's some very, very cool things that can be done with this, because you can actually, with the full ALMA, with these objects, resolve individual giant molecular clouds at redshift of 5, and study star formation in giant molecular clouds at redshift of 5. And even, one of my crazy, I have a crazy paper, which says that the different submillimeter lines, carbon line and the CO lines, have different, their rest frequencies have different dependence on the fine structure constant. And so if you have these very, very narrow lines from individual molecular clouds at CF5, and you look in different directions, you could potentially detect a difference in the fine structure constant in different parts of the universe. And there is an assertion that there is a gradient in the fine structure constant across the universe. It's very statistically marginal, and how could you possibly believe it? But if it's true, it will be easily confirmed by ALMA, I'd say, within the next 10 years, because you'll be able to just study the, since these lines have different dependence on the fine structure constant, you don't actually have to measure the redshift, you just have to measure the line frequency ratios, but you have to be sure that the lines are emitted from the same region, and that's why you need this magnification.
What are we seeing in the red? Is that CO? Is that continuum?
This is continuum, but we've also done carbon-2 in a lot. The carbon-2 line from these things pops up in about 4 seconds on ALMA. It's just amazing. And you can do nitrogen too. You can do all of the famous cooling lines of the submillimeter if you're willing to integrate for an hour. It's very hard to get a whole hour of ALMA time now, but in the future, of course, that will become routine. And studying these things, doing all of the lines with the different ALMA bands is going to be, a big deal. And there are hundreds of these things, perhaps even thousands of these. Some are brighter than others, but some of them are magnified as much as a factor of 50, and that gives you well over a factor of 1,000 in observing time advantage. So galaxy clusters. So now I have a Elvidge effect. So this is the effect where you have the microwave background, and then in a cluster of galaxies, as all good X-ray astronomers know, it's filled with hot electrons, and with fairly small probability, 1% or less probability, a microwave background photon might interfere with a hot electron and gain energy and be scattered. And so since it's scattered, when you look at the cluster at long wavelengths, at low frequencies, you see a reduction in the temperature of the microwave background. You see a little hole, and then at 230 gigahertz and above, you see a positive excess power. We only go up to here because in here it's hard even at the pole, but this is a nice null point because if you see the effect here and here, but not here, you're really seeing something. So, and one important thing about this is that the size of the signal, the detectability of the signal, is essentially independent of redshift. And because of cosmological magnification, just from the size, the change of size of the universe, almost all clusters of galaxies are 1 arc minute. So if you see a 1 arc minute defect, it's almost certainly Sunyaev's Elvidge effect. And at low redshift, it's real easy to get an X-ray image, but as you get up to z of a half, it gets a lot harder because the X-ray is going down like z to the minus 4. And by the time you're up at z of 1, it's a really major deal to detect one of these things, whereas the Sunyaev's Elvidge effect is basically the same, and the detectability is the same, provided you've got an arc-minute beam. So how do we find these things? Well, we have the 3 frequencies, and you shouldn't see it here. So this is, you see nothing here. You should see it pretty strong here and not as strong there. You combine these, and you can get a possible SZ detection and a statistical significance. The statistical significance, as it turns out, is a very good mass proxy. Not perhaps the best. I mean, there are big arguments about this, and you could ask people who do clusters about, well, they're willing to debate it for hours. But you can roughly, you can find these things and you can list them by likely mass, and then go out with the big optical telescope and make sure, oh, is there a cluster there or not? So in this way, now there are more than 1,000 clusters found. The first cluster discovered by the SZ effect was only in 2008. It was by us, by South Pole Telescope, Staniszewski and et al. And now there are over 1,000. Planck, of course, does the whole sky, but it's only a tiny little telescope and can't get out here to the high redshift things, which are smaller. South Pole Telescope are these black crosses. We kind of cut out where these things get too big. We just don't bother with them anymore because we know they're at low redshift and they can be found by other people. ACT, I don't know, ACT is kind of all over the place and has very, very many fewer than we do, mostly because of the site. They're good instrumentalists, but it's a crummy site. And so this is the current status. This lower edge here in mass, so this is simply the result of us cutting off the signal to noise of our possible detections at some value and not looking at anything down here. But in the new system, this is all going to get filled in, and it will be filled in by thousands of galaxies. We have 3 clusters here, which are at redshift above 1.6. We don't know quite exactly how far above redshift 1.6. And in future, they'll be going out beyond 2. So here's a pretty cute picture. Best of SPT clusters. Notice that all of these are named after CFA postdocs. And if you're a CFA postdoc and you want a cluster of galaxy named after you, come see me. So these are very massive clusters, and they're part of our big sample. We have some really interesting ones. There's the Phoenix cluster, which was more of an MIT project, but the cluster discovered by SPT, and it actually has a cooling flow and a lot of star formation. It's a very interesting cluster. Of course, a lot of these things have been observed in collaboration with the Chandra group here. And there's a project, SPT-XVP, which has done, I think now actually 100 clusters. And in combination with other results from lower redshift, we're now getting into interesting aspects of cluster physics. Are there cooling flows? What determines the entropy of a cluster? Are clusters really since Z of 1, are they all the same? And what went on before Z of 1? And in future, we'll have a lot more clusters out here, and we'll be able to deal a lot better with this kind of thing. So the final bit of science is measurement of the CMB lensing potential. So this is a picture of one of the deeper fields, and what we've tried to calculate here is the gravitational potential along the line of sight, which has distorted the microwave background. And this is the way this can be done best is in polarization, because the so-called B-mode polarization, especially on small scales, is almost entirely due to this effect. And so detecting B-mode polarization on the scale, which we haven't really done yet, will allow us to determine the lensing potential. So here's a kind of preliminary picture. So this shows our estimate of the lensing potential and compared it to the integrated surface density of infrared galaxies. And they're very highly correlated. This, of course, is gigantic. These are 1 degree resolution, but in the end, we will be down at the 3 arc minute level, and we'll be able to do this kind of thing at the 3 arc minute level with signals to noise in excess of 50. So this is going to be a very big deal in future. Greater than. Okay, well, the future. This is just one of these slides about technology, and the point is that the sensitivity of bolometers over 50 years has been declining in a Moore's law kind of way. But the fact is that for CMB studies, you'll never get much below here simply because you actually have the CMB as a background noise. And so we are currently doing close to about as well as you can do. And what that means is that if you want more sensitivity, you've just got to have more bolometers. And so in SPT, we've had a series of detector focal planes with more and more bolometers. So Akbar, which is an old South Pole, we saw that hanging off the crane there at the beginning, had only 16 detectors. Initial SPT system, 960 detectors, only only 830 of them actually ever worked. The current SPT system is only 2 frequencies, but it's polarization. So there's 150 gigahertz and 90 gigahertz. These have just been, one replaced the other in that giant red doer that hung off the Volkswagen thing with the mirror in it. So then there's SPT3G, and the guys at Berkeley have figured out how to stack bolometers on top of each other and do multi-frequency bolometers, multi-chroic pixels. So you design this very broadband antenna, and then you pick out the different bands with filters that are done and shot in a strip line in the same photolithography process, and put the Josephson junction detector on that, in that filter, and you can get 2 polarizations and 3 frequencies all simultaneously with 1 pixel done by photolithography. And so you can, clonk these things out with the photolithography machine and tile your detector plane in it. And then, thankfully I designed the telescope so that it has this huge field of view, and you stick these things in the field, in the focal plane, and there you go. So here's the new optical design. In this case, the secondary is not cold like before, but we have an actual Leo stop. So the image plane is now so large that we really couldn't do the doer like before. This is just a flat to fold things down. This, of course, this angle is determined by the Dragoni relation, and so you can't get away with it. But unfortunately, that sticks the end of this up here if you don't put a mirror reflecting it. So you put a mirror in there, and you take a little bit of extra loss from the flat mirror. The glory of this is that you have a Gregorian focus back here. If you take that mirror and slide it out of the way, you put your Event Horizon telescope back here, and you can switch from this system to the Event Horizon system, in 30 seconds under computer control. So there's this giant doer. So this is like 7 feet high here. This is like 6 feet. And it's a cryogenic doer. The lenses, the 3 lenses are made of alumina, and they're at 4 Kelvin. And this optical design, if I do say so myself, is absolutely astonishing. I just wouldn't have believed it, because each of these lenses is doing several jobs. Right, we've got a telecentric focus here. We've got a really high quality Leo stop, and we're simultaneously correcting the coma of this very large field of view at the Gregorian focus. So it's just mind-bogglingly amazing that it works. And these lenses are simply plano lenses. They are A-spheres, but it's a simple plano lens. Of course, it's that big in diameter in this doer. And it just blew me away that this actually works. Well, it hasn't worked yet, but the computer says it works. So this will give more than an order of magnitude. So at the moment, we're here, this speed 2.5. With this new system, we're going to be more than 10 times. We're going to be 20 times faster, and everything will go 20 times faster, including B mode detection and being able to get down to very low values. So the predictions are that we will in fact see B mode, and we will see if we can get, if we can actually do the difference between points that are separated on the sky by as much as a degree, which I think we can. We will see, make a good determination of R, and then there will be many, many more clusters of galaxies. So there's a combination of real data and fake data. So the real data are the black X's, and the Planck data, the red, that's real data. Then the blue is the expected results from the SPT3G survey, which will start perhaps as soon as next year, although things are not going as fast as I might have liked. So, in conclusion, the future of the SPT. The SPT will be the premier CMB telescope for the next decade. There's just no other telescope that comes close in resolution or sensitivity. Even if you put a 10 meter in space, you couldn't do a lot better than we can. And, you know, we consume like 50 kilowatts of power continuously, which is very hard to do in space. And, you know, we can go in there and tweak things and fix them. And South Pole is, you know, just not a lot worse than space. They're and a lot easier to get to. There's a lot left to do. I mean, this is the golden age of cosmology observations, but the mass of the neutrino, constraints on the era of recombination, history of dark energy, the current value and the historical value, thousands of galaxy clusters, even at redshifts up to 2, and at masses down to the massive groups. More of these lensed galaxies that are grist for ALMA. And then the CMB lensing potential with, say, 3 arc minute resolution and signal noise of 30 or 50, and a measurement of the tensor scalar ratio. And then finally, we're this station in the Event Horizon Telescope. So that's the end. Thank you very much.
Thank you very much, Tony. That's fantastic science. Do we have any questions for Tony? Rowan.
How are you going to deal with the dust problem?
As well as anyone else, you know, we will have a 230 gigahertz. And BICEP only has the 150 gigahertz frequency. We have 90 and 220, so we can detect dust ourselves simultaneous with the rest of our observations, and we can detect dust polarization ourselves simultaneous with the observations. I think the conclusion of some of the current BICEP brouhaha is that BICEP, you know, picked a spot which is well known to be fairly free of dust, but unfortunately is not really free of polarization. So the polarization in the galactic cirrus varies differently from the amount of galactic cirrus, and there are better spots in the sky. So either we will, you know, be able to deal with it as well as anyone else, or we won't. In which case, the measurement will be impossible. I mean, you know, you have to send a probe out beyond the galactic plane or something.
On this polarization, it looks like you're measuring the I and the Q Stokes parameter, but not U. Do you rotate that to measure U, or do you not care?
We do not. We own. The antennas, the adjacent antennas are actually rotated differently. So the adjacent ones will have different sensitivity to different polarization directions. And, you know, there's 16,000 of these things, and they're all oriented differently.
Thanks.
I have a question about those high redshift galaxies. A week ago, there was an ESO press release on an ALMA detection of redshift 7.5 galaxy. And basically, you say that there should be many of them and they should be quite easy to detect because they're bright in
Yes.
that sub-millimeter. However, there's only one so far. Do you know why?
Well, you have to be they're rare, right? There's like 1 per 20 square degrees of these things that are lensed by this much. You have to have, you know, a galaxy in you know, at Z of 5, and then you have to have another one at Z of a half right in front of it.
That one was in April 1689, the cluster that you showed in one of your.
Well, most of ours are not lensed by clusters; they're lensed by individual galaxies.
Oh.
So you have to have 2 galaxies like ram right in front of each other, and it's a rare thing. So you know, there may in the end be 500 of these things. But it's of interest to have them all over the sky because you really want to do this gradient in the fine structure constant. You want them all over the sky in all different directions.
How much does a given percentage change in the fine structure constant change the rest wavelength of the C+ line, for example?
It's a couple kilometers a second. So I could.
For how much percent change?
I have a whole paper on this, so I can send you the paper. I don't remember offhand. I couldn't. If I told you now, it would just be off the top of my head. I'll send you the actual calculation. Gary was one of the early people with Charlie Towns who did calculations of the opacity of the sky above South Pole. It's one of the believers rather than deniers in the Antarctic astronomy.
The data volume for 3G is what do you expect sometime in the night? Or
it's about 100 gigabits per night, which is not too bad. We can do a lot of the processing on site, actually. With a small cluster of current microprocessors, you can do a lot of data compression on site, and then you bring the data out in, you just each year you pack a RAID array in by airplane and fill it up and fly it out. Yes.
So it's very exciting, the prospects you mentioned for finding all of these clusters with the SC effect, but as you say, they are rarer as you go to higher redshift, and also dark energy is maybe a little bit less dynamically important as you go to higher redshift. So sort of, do you expect clusters to really become a constraint competitive with the other ones we have in terms of precision on dark energy using?
Well, actually, the statistics of clusters between Z of 1 and 2 is a factor of 3 or so more sensitive to cosmological parameters and dark energy than the cluster census between, say, Z of 0.1 and 1. So, the Z of 1 to 2 clusters, actually, there's a lot of hope for getting some really significant improvements out of that. Of course, there is essentially no clusters at all beyond Z of 2, just haven't formed yet by that point.
More questions? We have time for a couple more. Anyone? Yes.
so is there ever any big science that would come from going beyond 1 arc minute, a bigger mirror?
Yeah, I mean, you could imagine putting a 30-meter telescope at the pole and putting, 50,000 bolometers at the focal plane. You might be able to get, sub-arc minute scale microwave background gravitational lensing potential from that. You'd also find a lot more. You'd really be heavily. You'd see the background of infrared galaxies that we see with Herschel, for example. I mean, it would start looking like a Herschel map, except at longer wavelengths. Right? So you see a lot of point sources, right? Because the bigger antenna just gets that much more sensitive to point sources, and so it's not clear that what you would find is new compared to the Herschel results. Of course, you could get a lot higher resolution. I mean, that kind of work with the infrared background is actually resolution limited, and with the bigger antenna, you could get beams of 10 arc seconds, and you'd have a lot less confusion, and would have a lot better look at the infrared background, particularly the very high redshift infrared background. there isn't really anything left of the CMB at that kind of scale, sub-Archimedes scale. We thought a long time about exactly how big SPT had to be, and 10 meters is really the sweet spot. And 10 meters just couples beautifully into the the smaller SZ profile of the smaller clusters of galaxies.
Okay, unless there's any other pressing questions, let's thank Tony again.